Hello friends, let's continue our problem solving. So we are going to look at problem 1973, count nodes equal to sum of descendants. In this video, we are going to explain a solution based on recursion. So this problem, the strategy is essentially the same as problems like 1120, 2265. So our plan is the following. First, we're going to digest the problem requirements, and then we do the analysis, and finally, we share the simple code. First, let's look at the problem statement. So here, we are given the root of a binary tree. We want to find the number of nodes where the value of the node is equal to the sum of the values of its descendants. So the second paragraph basically defines descendants. So in this problem, the descendant does not include the node itself. So here we have 3 examples. So example 3 is very special because in this case, the root has no descendants, so the sum will be 0, and the root value happens to be 0, so we return 1. In other words, we count this root. If the root value is not 0, actually we are going to return 0, right? So in the second example, so the output is 0. So if we look at the value at 2 in the whole root, then the descendant sum is 5. 5 does not equal to 2, right? And if we look at 3, the descendant is sum value is 2, and 2 does not equal to 3. But if you look at 2, the leaf, it has no descendant, so the sum is 0. So 0 does not equal to 2. Therefore, we return 0. And for the first example, so we are going to return 2. The corresponding nodes are 10 and 3. So for the node root, that is 10. So the descendant has sum 3 plus 4 plus 2 plus 1, that is 7. For the left subtree rooted at 3, so the node 3 has value 3, and the 2 descendants are 2 and 1. So 2 plus 1 equals to 3. Therefore, we have 2 in this example. So with that said, let's also quickly look at the constraints. So the number of nodes in the tree is given by the closed interval. So it's 1 up to 10 to the power 5, right? So 10 to the power 5 actually is a decent large number, right? So basically, if for leetcode problems, if you have some counting is like 10 to the power 5, basically the square time complete solution in general will not pass all test cases. So here the node values are bounded below by 0 and bounded above by 10 to the power 5. So with that said, we are ready to look at the analysis. So for this problem, the logic actually is rather straightforward. So we need to pay attention to 2 points. First, for each node, we need to know the sum of its descendant values, right? And secondly, if we can get this information, for each node we can get the descendant sum in values. So we need to update the count of nodes during the traversal, right? So we couldn't do multiple passes of traversals. That is not very efficient, right? So for the first point, we can use recursion. So here, the recursion is very suitable in the sense that we are dealing with trees. Tree can be defined recursively, right? So for point 2, we can use attribute or field because the solution method is within a class, right? That enables this choice. Or we can use non-local variables, right? So we are going to present both in this video. So now let's first look at this one. So I'm going to first use the field method to do the update. So next, I want to write a hyperfunction. I just call it f. So we write a node. So what we want to do is that for a node, so we are going to get its sum of its descendants values. So this can be very straightforward. First, I want to treat a special case, if not node. So in this case, we have no descendant at all. So we're going to return 0, right? So we don't need to update this self result for sure. Otherwise, we can initialize a result variable, this s equals 0. Then we are going to check the left subtree and the right subtree, right? But we don't know if the tree exists or not. So we want to check if node left. It means that we have a left subtree at least, right? So we can first get this L. So SL is F node left. So this basically tells L is the descendant sum for the left subtree, but it does not count the node value for node left, right? So we want to increment this S by L, right? Because all descendants of the left subtree are descendants of node itself. Then also we need to count node left value, right? So this is the one. Similarly, we do the right subtree, right? So we got right is F node right. Then I'm going to increment this by R and node right value. So the reason we do the check is this expression is only valid with the corresponding node left or node right is not null, right? So, but in practice, you don't need to specify this L or this R. You can directly do update, right? Like you write here F node left or here F node right. But here we want to make it more clear. So with that said, basically here we need to do a check after we find this. So we want to check if S equals the node value, right? Then in this case, we're going to do update as incremented by 1. This is the counting, right? And then for the function logic, we need to return this S. So once we've done that part, so we can call this function, right? So though we have returns for this function, but we use it as dummy. So you can write something like this, but it's not necessary. So let's just directly call this function, not for node. We need to call it for root. Then we just need to return self result. So notice that this code actually covers, in particular, the edge case for example 3, right? If we just have a single node, then we don't enter these two if blocks. S will be 0. Therefore, we will always make a comparison of this S itself with the node value. So because we initialize S to be 0, if node value or the root value is 0, so we are going to count 1, right? Otherwise not. So now with that done, let's first do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So as I mentioned, you don't need to specify L or R. Let's copy this part and write it here. Then I delete this line. And similarly, I can copy this part and put it here and delete this line. Then I can do a test. Yeah, it passes all the cases. So this can be regarded as version v1. So let's make it v1. And then let me copy this part. So in this version, I used the attribute or field to update the result. So now in the second one, I want to use nested functions. So I want to use non-local variable. So I define this result as a variable within this function scope. And then here, when I write this inner function, what I want to do is first I want to non-local a result. In other words, because this result is immutable, right? In order to update when we call this function, I want to non-local it. And then I want to change this part to be a result itself. And then here I just need to return result itself. So now let's do a test first. Yeah, it passes all the cases. Yeah. So that's basically about it for this specific problem. Actually, it's good to do or practice problems like problem 1120, problem 22, 65, and the current problem, let's see, 1973 together. or some other similar problems. So you can fill the pattern, or you can fill the paradigm. So with that said, I guess that's it for this video. So if you're interested, you can check out our channel and to practice more problems. We hope that the videos in our channel can give you some hints or encourage you to practice more so that you can get better. So with that said, I guess that's it. Thank you.